which means I won't be wandering around. And if you have any trouble hearing me, just let me know. This is also for the people on Zoom.
The attendance poll only says Zoom as an option.
Pardon me?
On the attendance poll, when it says like vote of attendance, it only has one option, Zoom.
Oh, okay. We'll edit that. Did you? Yeah. Okay, yeah.
All right, everybody, let's begin. Please shut your laptops, usual stuff. We'll continue with our series of lectures. We're going to have a slight change of topics. We've gone through different kinds of models. We learned initially that neural networks are universal approximators. They can model pretty much any function. They can check static inputs for patterns. They can scan for patterns for position invariance. And they can analyze time series for patterns. But then in every case, they must be trained to make their predictions. So when we actually train these models, what do they learn internally? What does the network actually represent? So today's lecture is going to look at this area, and we'll build on it over the next next few lectures to see how this understanding can be used to develop generative models. So here's the learning problem in neural networks. You're given a collection of input-output pairs, and these are your training data, a bunch of inputs, and the desired output for each of these inputs. You must learn the function from it. So again, using our usual picture, the mesh might be the function you want to learn, but all the data that you're provided are just these little red lines, and you must learn the function from it. So in much of the explanation that we saw during the semester, we assume that the data are somehow cleanly representative of functions. So when we want to learn to perform classification, for instance, if we wanted to learn to classify these, the usual double pentagon example where the output is required to be 1 inside the pentagon, double pentagon, and 0 outside, you expect to see a class of data instances inside the double pentagon, marked in red, and a bunch of data outside. And from just these data, you're supposed to learn the boundaries. But then in real life, they're never going to be so cleanly separated. You will have some leakage. So you would have some blue dots inside the double pentagon and some red dots outside. And you must nonetheless learn the boundaries from these data. So how do we do it? Now, to see what happens, let's back off to a really simple example, linear classifiers. Now, if you had two-dimensional, if you were working in two-dimensional space, then a linear classifier is just a line which has to separate out one class from the other. If you were to plot this as a three-dimensional function, it's going to look like a Heaviside step function. And you'd have to learn, can I just carry this with me? Possibly not. Okay. So you'd have to learn the classifiers from data of this kind, where you have a bunch of red and blue dots, and from these dots you have to learn the function, except that you expect to see that the separation is not clean. So you will see some red dots in the blue region and some blue dots in the red region. So how do we learn this function? So now again, to really understand this, let's back off one more step. Let's go all the way back to one-dimensional functions. So now the input is one-dimensional, and you have two classes, red and blue. Now, what is a linear classifier for one-dimensional functions? Anybody? One-dimensional input. Pardon me? It's just a threshold, right? You're going to have to find a threshold where everything on one side is assigned to one class and everything on the other is assigned to the other. Now, over here, can you find a threshold that that clearly separates the red and blue classes? You can't, right? Now, here's the other problem. We saw this earlier, that your neural network is a universal approximator. It can learn anything. It could learn this really ugly function that you see out here. Now, would you really want this function? This is a perfect fit to the training data, but would you want this function? Obviously not, right? And even if you said that this is perfectly acceptable, What would you do if you had a situation like this, where you had a bunch of data, let's say 100 points, all with the same feature value, the same X value, but some of them are marked as class 1 and the other rest are marked as class 2, class 0. Now what would you learn? So here obviously there's no threshold that can separate the two. There's no function that you can plot that's going to be correct for both sets of points. So let's say you have this situation where you have 90 instances of red and 10 instances of blue. What would you want your function to output at this value of x? Would you want it to just output red because red is the majority? Or would you want it to output a 0.9 to indicate that 90% of the data instances with that value of x are red? What would you prefer? What do you think makes the better, seems more sensible? The 0.9, because it's giving you more information, right? It's giving you the posterior probability of the classes. If I mark red as class 1 and blue as class 0, this is giving you the posterior probability. It tells you what fraction of instances with that specific value of x are class 1. But now let me change things a little bit. I'm going to perturb all of my data points just a tiny bit by 10 raised to minus 17, let's say, which is the resolution of floating point data. So no two points are identical in terms of x. They all have, but 90% of these points are assigned to class 1 and 10% are assigned to class 2. Would you now suddenly want the function to go up and down, or does it still make sense to say this must be, the output in this range of x must be 0.9? Which makes more sense? The second one, right? So now, continuing this, basically you accept that a small perturbation should not change the output. But then how large can this perturbation be before you begin changing your mind? So let's go back and look at this from a different perspective. At each point, let's look at a small window around the point. And now I'm going to plot the average value of y at that point. So in this example, when you're far out to the left, the average y value is just 0. So you're going to get a blue dot. As you keep moving forward, at some point you begin to see a few red dots. And at this point, the average is going to begin moving up. And then if you keep going on, eventually all points are going to be red. And so this function is, gives you a better idea of the posterior probability of the class 1 for any x. And so it kind of makes sense that you want a function that actually captures this characteristic. And what does that function look like? It looks like this. Does this look familiar? What is this? This is just a sigmoid. It's a logistic, right? And so indeed, that's what we have, right? This is your logistic function. And if you had linearly separable, or if you were trying to build a linear classifier for one-dimensional data, you would expect that they're roughly linearly separable, which means that there is some kind of a threshold where as you keep going further out, the number of points that you see from class 0 is going to keep decreasing. And when you go in the other direction, the number of points from class 1 is going to be decreasing. And so the overall probability of class 1 is going to follow a sigmoid, which is why we use the sigmoid. And here's the sigmoid. We are all familiar with the equation here. So it looks like so. 1 over 1 plus e raised to minus w0 plus w1x. Assume both w0 and w1 are positive. So if x is a very large negative value, then what is e raised to minus w1x? If x is a very large negative value, then e raised to minus x is going to be infinity, right? And so what will the overall function be? 0. If x is a very large positive value, then what is e raised to minus w1x? 0, right? And the overall function is 1. And so you can see the function goes from 0 at the far left to one on the far right, it sort of transitions smoothly from one to the other, which is why you get this sigmoidal shape, and it represents the posterior probability of class 1 given the input, of the class given the input for unidimensional data. And so when you have a sigmoid, a perceptron with a simple logistic activation function, this actually models the a posteriori probability of the class, of a target class, given the input. Now, there's a question over here that you're going to have, you probably would ask. As I plotted these dots, I said I was looking at the average y value within a window. How wide is the window? I have not specified, right? Clearly, as you make the window wider, those things are going to change. If you make them narrower, it's going to get noisier. So do we even need to consider it? We'll get back to this. Now, moving on from one-dimensional to now to a more generic two-dimensional problem. It's the same thing. You'd have some, if you want to build a linear classifier, you're going to have some data instances from class 0 on the one side, from class 1 on the 0 side. So there's no hyperplane, there's no line that's going to cleanly separate the classes. So we'd have a two-dimensional sigmoid, which basically looks like a sheet that folds like so. And when you're learning the sheet, you're basically learning the rate at which it folds and the orientation of the fold. Now, this function itself is still giving you basically the same kind of logistic characteristic that we saw for the one-dimensional case. But this, we claim, is a linear classifier. Why is this a linear classifier? Anyone? Why would this be a linear classifier? Anybody on Zoom? Can someone tell me? Guys, everybody's sleepy. So, Enzo, why is this a linear classifier? All right. Standing in front of the gooseneck is hard, so I'm going to go off, and I apologize to the guys on Zoom, right? So here is how it is. I have this sheet. So I have this sheet, and if I say choose a threshold, if y given x equals 0.5, what is the locus of inputs where this holds true? What would that locus be? Anybody? That's going to be a line, because we have 1 over 1 plus e raised to minus w0 plus w1 x equals 5, right? Or I can just take things over 1 plus e raised to minus w0 plus w1 x equals 2. I can take this one away. This is 1. Take the logs on either side, you're simply going to end up with the equation for a line, right? So the boundary between classes, although the function itself is curved, the boundary between classes is going to be a line. Which is why this is a linear classifier, although the probability itself sort of curves away from the line, right? And so now, again, we go back to the question, how wide must this window be when I begin to average things? Or do I even need to explicitly consider the window size? I don't need to. I can just use a statistical estimator. So the way you train it, assume you just have a single logistic, you'd be given many xy pairs, represented by the dots over here. And we want to estimate the W0 and the W1 of the curve, right? So what is this? I have it here. Sorry for going off here. I have P of y equals 1 given x is 1 over 1 plus e raised to minus w0 plus w1 x. So what is P of y equals 0 in this case?
1.
So P of y equals 0 must be 1 minus this, right? Which, if you work out, is simply going to become 1 over 1 plus e raised to plus. That means 0 plus w1 is. Right? Everybody with me? Can I write a common formula for both? Does this enable me to just write P of y given x? And you give me a formula? Someone? Yeah.
Have a -1 to the exponent for y, so the sign changes based on 0 or 1, basically.
It's much simpler. I can actually say, just use this y equals, instead of using a y equals 0 or 1 notation, I can use a y equals -1 or +1 notation. So the two classes are +1 and -1. And now in this case, this is +1 times, so y equals 1 is, y equals 0 is, e raised to +1, this is e raised to -1, right? So you will see the same, you will see the y on both sides. I can just write this as a common thing, which is y equal P of y given x is 1 over 1 plus e raised to minus y times w0 plus w1x. That's making sense to everybody? Right. And so once I have a nice closed form formula, I can go around to estimating things. And here's how. My training paradigm, I'm given a collection of training data, xy pairs. X's are the input vectors, y's are the classes. And now we use what is known as the maximum likelihood learning estimator. This is the most common approach for estimating probabilistic models. So if I give you a collection of data, and if I ask you to estimate a probability distribution for it, the way we would do it, we would assume some kind of a formula, parametric formula for the data, and then we are going to try to estimate the parameters of this model that maximizes the probability of the data that you have seen, because that means that the data that you have seen are most typical of the world. And so in this case, we are going to try to estimate the model to maximize the joint probability of all of our training data. Now, if you assume all the training data are independent, that's just the product over all training instances of the product of the individual training instances, probability of the individual training instances. And the joint of P of x and y can be decomposed using Bayes' rule as the probability of x times the probability of y given x. And so by our model, what was P of y given x? We just wrote that down, right? That is going to be 1 over 1 plus e raised to minus yi times w0 plus w1 xi, right? And so this is what we will try to maximize. Or alternately, we're going to take the log of this probability. The log is a monotonic function. So if you increase the probability, you're going to increase the log probability. And also, which means the parameter setting at which the probability is maximized is also the parameter setting where the log probability is maximized. The nice thing about logs is that this multiplication simply becomes summations. And so the log probability that you're maximizing is the sum. The sum over all training data instances of the log probability of x plus the sum of the log probability of y given x, which is just a logistic function according to our model, right? So this is what we'd maximize. And so training our model means we are going to maximize this log prob, which is that we will be estimating W0 and W1 to maximize the log probability of the training data, but then the log probability of the training data has two components. This first component is not dependent on the model. It's just the probability of x. So all you're left with is the second component, which means we only need to maximize the sum over all training instances of the log of the logistic function computed at that x, right? or alternately minimize the negative log. And if you look at the equation at the bottom, you would recognize this as just the KL divergence between the output of the logistic function and the actual probability of y given x. And so this is what we find is that when you perform maximum likelihood training of the logistic function using your training data, which is a very standard and fairly rigorous statistical procedure for learning probabilistic models, you end up doing exactly the same thing that you would do when you're minimizing the KL divergence or the cross entropy. So if you were training your logistic function using backpropagation and the methods that we've seen in class, what we are actually performing is maximum likelihood training of a model that does a good job of predicting the probability of y given the input x. So that was for a linear classifier, right? But then what about something more complex like this, like the double pentagon? Again, remember, we said that when you want to train the double pentagon, you're not going to get clean data. You're going to get some red dots on the blue side and some blue dots on the red side. So how do we train this? Before we even get here, let's look at the clean case, where there are no red dots on the blue side and no blue dots on the red side, right? Let's also assume that I have the perfect architecture. Now, you'll remember from lecture 2 that I can use this architecture for training the classifier, right? This first subnet captures the first pentagon. The second subnet captures the second pentagon. And the unit on top, it's an OR between the two, right? And now, what's the outermost, the topmost neuron doing? That's a perceptron, right? And if I were using a logistic activation function over there, what kind of classifier is it, the perceptron on top? Come on, we just mentioned it, right? What kind of a classifier is a logistic function? Can you say that aloud, please? It's a linear classifier, right? So it only does a good job of classifying data. It does a perfect job of classifying data if the two classes can be separated by a line, right? So now, if this network does a perfect job of separating the red from the blue, then what does it tell us about what kind of data this guy is looking at? Specifically, if you look at the outputs of these two neurons over here, that's what the uppermost perceptron is operating on, right? So in that space, what do you think the data will look like if the network is doing a perfect job? Yeah, so what? No, but out here, by the time the data get to those two lines that go into the final logistic. Pardon me?
1 or 0.
They won't be 1 or 0. They must be linearly separable, right? Otherwise, the outermost, that guy is not going to be able to separate the reds from the blues. So what this means is that I can think of the network as having two distinct components. The first component manipulates the data. It just moves it around from the double pentagon arrangement in the input space until by the time it's out at the end of this block, the data look like that, so that the reds and the blues are linearly separable. Then the final classifier can actually separate the reds from the blues. So, that making sense to you guys, right? So, this means that this portion of the network, which goes up to the penultimate layer, everything except the output layer, it can be viewed as a transformation that transforms the data from nonlinear classes to linearly separable features. And so this, wait before we get here. So this we said was true for sufficient structures, right? That's what I started off assuming. Even if the network is not sufficient. Now, if the network has, insufficient structure, which means it has fewer perceptrons than is required, than the minimum number required for this data, what would happen? Again, the outermost, the outermost neuron, the logistic regression, is trying to separate the classes. That is a linear classifier, which means that the rest of the network underneath is going to work really hard and try to make the data, the two classes, as linearly separable as it possibly can, so that the final neuron can do the best possible job of classifying separating the two classes. But if the structure is incomplete, is insufficient, all this means is that that final neuron will not be perfect. It's going to fail to separate perfectly, but within the limitations of the architecture. Ideally, it will separate as best as it can, the lowest error possible. So here's your first poem. Okay, 10 seconds. You can't find the second poll, can you check 1056?
The first one. Cannot find the first.
1055, it should be up. They were up last night. No? Okay, never mind. Can someone on Zoom tell me the answer to the first question? It is on the slide. Do we have someone on Zoom?
It's true.
It's true. Zoom, what about the second question?
True.
Let's see. So the portion of the network until the second to last layer is essentially a feature extraction module that extracts linearly separable features from the data. And the output layer in your network is a linear classifier that will only perform well if the rest of the network successfully manages to separate the classes and transform the data so that they are linearly separable. So that's when the data are linearly, okay. If the data are separable and can be modeled by your architecture, then the lower portion of the network is going to try to make them, transform them into a feature space where the classes are separated. And then the output neuron is going to learn to classify them, right? So this person at the back, can you turn your phone upside down? You're allowed to do your homework. You should go outside, that's all, right? Now, if the network is not sufficient to separate the data, or if the data are not separable, then the remember that we're actually performing a maximum likelihood classification, right? So which means it's going to try to learn the distribution of the data. So the feature extraction portion of the network is still going to transform the data such that the posterior probability of the class given the input is maximized, even when the data are not separable. So that's how the whole thing operates. And so if you have inseparable classes with an output logistic perceptron, the output logistic computes the posterior probability of the class from the output of the feature extraction layer, which is the posterior probability of the data given f of x, right? And again, as in the most generic case, if it's a one-to-one function, then p of y given f of x, that's basically the same as p of y given x. And so for any class, which means that even if the function, even though you actually have a fairly nonlinear neural network, which is operating on the data and is finally classified using a logistic regression, the overall network is actually a statistical model which computes this term. It learns to compute the posterior probability of the classes given the data X. So what does the network do? The network is a statistical model that learns to compute the posterior probabilities of classes. And so when the data are not separable and the boundaries are not linear, the output is P of y given X. For multi-class networks, it will be a vector of posterior probabilities. And if it's trained to minimize the KL divergence, the parameters of both the final logistic and the network are learned to maximize P of y given X, meaning it's actually a statistical model. And what we are performing is maximum likelihood training of the network, which is a statistical estimator. So the neural network is not just any odd function, it's a statistical estimator, yeah.
So are we looking at densities at different points?
You don't need to, right? You're looking at P of y given X because the P of X is not a function of the network. So so you don't really model P of X, you just model P of y given X. Regardless, you're doing a maximum likelihood estimate of the component of the components of the distribution, namely the parameters of the model, to best explain the data. Right? So here's the second point. Okay, 5 seconds. Someone on Zoom, is that first statement true? Zoom?
Yeah.
Okay, what about the second one? True or
Yeah.
false? You guys here, how about the third statement, true or false?
False.
And the fourth? So the first, second, and fourth statements are true. So for example, you could train a network. Now, if you think of the network as combining a feature extractor with a linear classifier, once the network is trained, you know that the feature extraction portion of the network has derived linearly separable features from the data. So now, if you use that as a feature extraction, now you can extractor, then you can subsequently use any linear classifier like a support vector machine to perform classification. So a classification network is just a statistical model that computes the a posteriori probabilities of the classes given the inputs. Training the network to minimize the KL divergence is the same as maximum likelihood training of the network. And it doesn't depend on the actual linear separability of the classes, and it is indeed valid and sometimes beneficial to train the network and subsequently replace the final linear classifier with some other linear classifier. So here's the story so far. A classification multi-layer perceptron actually consists of two components. There's a feature extraction network that converts inputs to linearly separable features or nearly linearly separable features. And there's a final linear classifier that operates on these linearly separable features. And if you use a softmax, the final layer of the network is actually a probabilistic model which computes the a posteriori probability of the classes. So training the network to minimize the cross entropy loss or the KL divergence basically performs maximum likelihood training of the network to best estimate the posterior probabilities of classes for any input, which makes sense. You want to be able to present a picture and ask the network, what is the probability that this is a cat? And that is indeed what the network is learning to compute. So far so good. We've seen what happens at the final neuron. That's a linear classifier. We've seen what happens at the penultimate layer. At the penultimate layer, the net portion of the network from the input until the penultimate layer tries to derive linearly separable features. But come on. But what about the rest of the layers through the network? What happens there? Now, there are several hypotheses to this, but then the one that kind of makes most sense is what I call the manifold hypothesis. Think about the double pentagon problem. You had data within a pentagon, a double pentagon, and data outside. So this is clearly not linearly separable. The two classes are not linearly separable. So what is the network doing? As you go through the various layers of the network, the data keep getting moved around so that they get increasingly linearly separable until when they arrive at the final layer of the feature extraction portion of the network, they are actually as close to being linearly separable as possible. So here's a nice visualization of how this works, right? In this case, we have a small problem. We have a simple problem, which is we have data which are separate. We have a circular decision boundary, and the data are separated into two classes, the portion of the data inside the boundary and the portion outside, right? And now we want to train a network that can perfectly classify the portion inside the circle from the portion outside. The network itself has only the data are two-dimensional. The network has three hidden layers. The one hidden layer with 3 neurons with tanh activations. And then the output of these neurons goes into a final logistic function. Now, what happens to these data? Let's just visualize this, right? Again, I pardon for going away from the gooseneck, but yeah. Let's consider this. If I have so if I have data on this is a two-dimensional plane. That now, let's consider what happens in the network. We have data X, which is 2D. This is put through a 3x2 matrix, which is a linear layer, which gets you the three-dimensional Z's. These are in 3D. These are put through a tanh activation. And then you get the Y, which is still in 3D, right? And then you get a linear layer, which is 1x3, which gives you a new Z cap, which is the logistic, which is the logic, which is in 1D, and then you get the logistic, right? This is the sequence of operations that we have. So now, if I start off with a two-dimensional plane, and then transform it using a 3x2 matrix, what is the dimensionality of the output? What is the dimensionality of the data when I transform two-dimensional vectors using a 3x2 matrix? Yeah. It's going to be, yeah? How many components do the output have?
2 plus 3.
So if I have a two-dimensional vector, xy, and then I multiply it by a 3x2 matrix, how many components is the output? 3 cross 1, it has to be 3, right? So if I transform this entire two-dimensional plane using a 3x2 matrix, what is the output going to look like?
3 cross 2.
3
cross 2.
I'm transforming an entire plane by a 3x2 matrix. What happens? Guys, you're being very sleepy, yeah?
Vector.
Is it going to be a vector? No.
You're moving to higher dimension, 3 dimensions.
It's going to move into 3 dimensions. So what will it look like in 3 dimensions? So I've multiplied this by a 3x2 matrix, which means every point on this plane has been multiplied by 3 cross 2 matrix. So every point has gone from being in 2 dimensions to being in 3 dimensions. So now this is going to live in 3 dimensions, correct? Is it going to fill up the 3-dimensional space? Then where is it going to be?
On a single plane in the 3D.
It's going to be on a 2-dimensional plane in 3D. You're not adding new dimensions, right? So this guy is going to be on some 2-dimensional plane in 3D. Right? Everybody with me? So now, if I put this, that's Z. Right? This. Now I put this plane through a tan H activation. So every point is being transformed. Now what happens? What will happen to the plane? Disperse, shifted. Every point is being, the values are being transformed non-linearly, right? Some points are being stretched more than others. So what will happen? It will curve. So once I put it to the tan H, this is probably going to become something like some shape. I'm not really sure what the shape is. We will visualize. It's going to bend the surface. That makes sense? Right? And so now I have a curved surface in 3D. Correct? And then I multiply this curved surface by a 1 cross 3 matrix. What will happen to it?
Vector.
Every point is going to become a single line, right? So any point in the space, I'm just going to be left with 1 dimension. So it's basically, this would be a weight vector, and you're projecting your data onto the weight vector, right? And it's going to take some value. That makes sense to everybody? And so let's see what really happens over here. I'm going to show a little animation. And this is what happens as you train it. So as you train it, you're going to learn the weight matrix of the first layer, right? And that is going to figure out how to position your 2-dimensional space in 3D space. So there are 2 things happening here. Several things happening. The first linear layer is positioning the 2D spacing, the 2D plane in 3D space. Then the activation is warping it. Then the second linear layer is projecting all this entire warp surface onto this line. And the only way a linear classifier is going to work perfectly is after projection, everything within the circle falls on one portion of the line and everything outside falls on the other portion of the line. That makes sense? Right? And so the network is learning how to position the plane in 3D space so that when it's warped by a tan H activation, the subsequent projection actually separates out the points within the class from those outside. And so again, if you take a look at it, this is basically what's happening over here. You can see how the plane keeps getting moved around until the warped surface can be projected into 2 distinct regions of the 2 classes on the warped surface can be projected onto 2 separable regions of a line. So this is what the network is doing. Now in a more complex problem, it's a more complex version of the same thing. And so here's a more complex example. This is the SIFAR 10 problem. So here you have data of you have points in many different colors. Each color represents a different class. This network has 11 layers and a final classification layer. So initially, when I just initialize the model is random. So all the data points are going to be scattered all over the place. Now I've projected the hidden layers down to 2 dimensions just for visualization. And you can see what they look like, right? So now let's see what happens as you train the model. The animation is a bit too fast, but you can see that once you train the model, as you go through the layers, the classes begin to get separated. And so by the time you get to the 10th or the 9th or the 10th layer, the classes are now linearly separated. You can draw lines to separate the classes. And in fact, this is more visible if you do this in 3 dimensions. the visualization. And you can see that as you go through the layers, each layer operates on the data and moves it around to increase the linear separability of the classes, till eventually they're as separable as possible. Now here, observe something interesting. The classes are already linearly separable in this case by layer 7 or layer 8. Additional training, so what are the additional layers doing? In fact, if you just put a attach a linear classifier to this guy, right here, the classes would be perfectly or nearly perfectly separated, classified. So the additional layers are actually moving the classes further apart, as you can see. And so when you increase the depth of the network, when you train the network, as you continue to train it, initially the classes are going to be linearly separable at the outermost layer. Then as you continue, the layer at which they become separable keeps moving lower and lower down. And so in fact, if you train a layer and then you chopped off the top few layers and then attached a softmax, it would still be a pretty good network. And in fact, this is one of the techniques that people often use to reduce the size of networks. So yeah.
Why don't we move beyond 3 dimensions?
This is just visualization. The actual data is in many, many dimensions. It's, I think, this one was, I don't remember. It's about 100 dimensions down to 3, yeah.
I know we're talking about like the number of layers and like afterwards like a certain amount like it separates them further.
Yeah.
But what about like the width of the layers? Like does that how do we I guess like can we reduce that afterwards? Or?
So yeah, you could possibly, but then what we're speaking of is what has happened to the layers. Now go back and look at this. If I start off with 2-dimensional data, in my example, I've converted this to a plane in 3 dimensions, right? And so I could have converted to a plane in 4 dimensions. And the principle still holds. The more the number of dimensions, the greater the flexibility I have to adjust things. And so you might well find that some of the dimensions are spurious, but then if you think about it, a 2-dimensional plane in 4 dimensions is not necessarily going to be of the kind where you can just throw away a dimension.
Yeah.
It's going to occupy all the dimensions, although it's in 2 dimensions. Right? That answer your question?
Yeah.
Yeah.
So what happens if we just have one layer with exponential number of neurons? Like
We're just going to be projecting it into a very high dimensional space, right? Here it's 3, it could be 200. The same principle still holds. Any other questions? Anything on Zoom? No, okay. So far so good, right? We have an idea of what happens inside the network. We've seen what happens at the outermost layer. It's a linear classifier, but it actually computes posterior probabilities. We've seen what happens at the penultimate layer. The network until the penultimate layer is trying to extract features which are linearly separable. We've seen what happens as the data goes through the network. It tries to make the data increasingly linearly separable. But what does the very first layer learn? Or what do the individual neurons learn? For that, let's go back and look at the perceptron again. So here's the basic perceptron. And I'm just going to assume for now a threshold activation perceptron because it's easy to explain, but all the lessons transfer to other activations as well. So here's what the threshold perceptron did, right? You computed a weighted sum of the inputs, and then you compared the weighted sum to a threshold. If it exceeded a threshold, the output was 1, otherwise it was 0. So I can write it like so. We saw this in earlier classes. If I write my input as a vector x and my weights as another vector w, then the weighted sum of the inputs is just the inner product between the weights and the data. And so when I compare this weighted sum to a threshold, I'm just checking if the weighted sum, if the inner product exceeds a threshold. Now, what do we know about the inner product of 2 vectors? What does it capture? Anyone? Come on, guys. What is it? Yeah.
Just a value.
It's just the angle, right? So here's the thing. In very high dimensional spaces, all vectors are more or less the same length. So it's just a characteristic of data. If I restrict the length of my data to anything, say 1, then as you increase the dimensionality of the data, the volume of the, consider a unit sphere. The volume of the sphere that's close to the surface keeps increasing. And at very high dimensions, basically the entire volume of the sphere lies at the surface, very close to the surface, which means all vectors are basically the same length. So now when I compute the inner product of two vectors, if I have W transpose X, this is simply magnitude of W, magnitude of X, cos of theta, where say this is W, and this is X, and this is theta. That's the inner product of two vectors, right? And so for any class, when I say that, when I'm comparing the inner product between the feature X and the weight W to a threshold, I'm literally just saying cos theta should be greater than T over the norms of the two vectors, assuming the norms are all more or less the same. Basically, you're just considering cos theta. You're saying that the angle between W and the vector must be less than something. So in effect, you're saying that if your data lies within some angle of the vector, then the output is 1, otherwise the output is 0. So what does this make the vector in this case? Similarity, what does it make the weight vector? Anybody? I'm saying that everything, if the angle between my data and this vector is less than some angle, some theta, I'm going to output a 1, right? So in other words, you're saying that any data, which if I have a weight vector W, you're identifying a sphere, a circle, a radius, and anything within that radius is going to be found to match. And what is the weight vector W itself? That is a representative of that region of the space. So the vector W can be thought of as a template for the class. And you're matching all of the inputs to the template. Make sense, right? So in effect, what you're really computing is the correlation between W and X. And if the correlation exceeds a threshold, you're going to, the unit will fire, otherwise not. Now, once you understand this, it's very simple. You can begin building things. So let's say you had one of those old LED grids that you used to have in ancient watches, digital watches. And you wanted to recognize if the digit was a 2. Then what would you do? You would create a template that looked like the digit 2. And then anytime you got an input, you would compare your input to this template. And the way you would compare it is by computing an inner product between the two, the correlation. And so if this here, if the input is red pattern, the template for 2 is shown in black. The inner product, the correlation between the two here is just 0.57, so you'd have a threshold. It has to be at least 0.8. It doesn't match the threshold, so this is not a 2. Whereas if you had something that looks like this, here the correlation is much higher, 0.8, 0.82. And so you'd say this looks like a 2, right? In fact, for any pattern that you'd want to recognize, all you would have to do is to just draw the pattern that you want. And that becomes as your template, and that becomes your set of weights. So what this tells us is that if I have an MLP, the first layer neurons, these are just simple perceptrons. And then again, we see that the perceptrons in turn are correlation filters. Their weights represent typical patterns that you expect the input to match. And the neuron fires if the input matches these weights. And so here, if I have a larger network, and let's consider the simple business of recognizing if the input is a digit or not. So I have, let's say I have the same LED grid, and I can have weights 0 through 9 on this grid. And I want to build a network that looks at this figure and tells me if this is a valid digit or not. If you build such a network, what would the first layer neurons learn? the first layer neurons are going to become feature detectors. The weights of each of these neurons are going to represent a pattern that the neuron is trying to detect. So you might find, for instance, that the first neuron here, the weights end up looking like this. It's looking for horizontal patterns, right, at the very top. Maybe the second one is looking for a vertical bar to the right. So the weights would look like a vertical bar to the right. Maybe the third one is looking for a vertical bar to the left. So each of these neurons is going to end up representing one pattern that it's actually looking for in the input. The subsequent, neurons in the subsequent layers will look at combinations of the outputs of the first layer neurons. So here, for example, the second layer neurons might be looking at, do these patterns combine to form the digit 1? Do these patterns combine to form the digit 2? And so on. And the final one is, of course, ORing them all to decide if it's a digit, valid digit. So once you realize this, here's something I can do. I can train this network. And now, having trained this network, I throw away the upper portions of the network. I just keep the first layer neurons. And then, for any input, so again, consider this. If I have so suppose I have some input, and the input is, say, something like this. Let's see, okay? Now, actually, let me just make this horizontal vertical patterns. So let's say that the input is just this guy, right? Just these three. Now, will that first neuron fire if the input is just this? Yes or no?
Yes.
Okay, so now let me create an empty grid on the other side. And if the first neuron fires, I just inspect its weight pattern. Because the weight pattern tells me what it's looking for, right? And fill in the weights away. Will the second neuron fire?
Yes.
Yes. So what must I fill in over here? Something over here. What about the third neuron? Will that fire? So do I need to do anything on the right hand side? What about the fourth? Will it fire? Fifth? Sixth? What about the? And if it fires, what must I fill in? The horizontal bar, right? So what have I done over here? I've basically just looked at the outputs of each of these neurons, which here I'm assuming is 1 or 0, but it doesn't have to be, right? And then I've multiplied the output of the neuron by its weights and filled it back in, right? And what will I be reconstructing? What happens if I do this for all of the neurons? Come on, guys. I'd be reconstructing most of the input. Would I be reconstructing it completely? So what would I reconstruct?
You'd be reconstructing it with the
So
features that have been extracted.
you'd be reconstructing those features of the input that have been extracted. In this case, you'd be reconstructing features that are relevant to classifying whether it's a digit or not. But nonetheless, here is the situation, right? If I just, so what does multiplying the output by the weight mean? It's like having the transpose of the weight matrix on the outside, going back to the same dimension as the input, right? And so, if all I did was this, I put the input through this network, captured the hidden representations, multiplied by them by the weights, transpose of the weights, and combined them back, you're going to reconstruct something that looks pretty much like the input, because the input layer, the first hidden layer, has captured all the features, relevant features of the input, and then I'm just reconstructing these features. This makes sense? Okay, so now here, I'm only going to be reconstructing those features that are relevant to classifying digits. But then if I have if I actually am more interested in reconstructing the input itself, then what would I do? In this problem, the network is optimized to recognize digits, only retains distinctly digit-like or obviously not digit-like features. The remaining features would be irrelevant or would be lost. But I can try to make this explicit. I can say, learn my features so that when I put them back together, I will actually reconstruct the input. This is what is called an autoencoder. So here you have a portion which has feature detectors, which detects various features in the input. This is what we call the encoder. And then we have a portion that recomposes these features to reconstruct the input. And that's what we call the decoder. Now, the simplest autoencoder, I have a complex one here, right? The simplest one would just have one hidden neuron. And to make it simpler still, I'm going to assume that that hidden neuron only has a linear activation. So I have this one hidden neuron here. It just takes in a y, the input, and computes w times the input. The activation is identity. And then I'm multiplying the output activation by the weight matrix, and I'm trying to reconstruct the input. What will this learn? Now, I'm going to explicitly train this to minimize the error between the reconstruction and the input. So if I do this, what will it learn? Here's what I'm doing, right? The hidden representation is Wx. I've multiplied that by W transpose. And so I'm trying to minimize the error between x and x hat, which is x and W transpose Wx. Does anybody recognize this? What is this actually capturing? Anyone? How many of you are familiar with principal component analysis? You must have heard of PCA, right? So what is this doing here? Pardon me?
Centering the data.
I'm just projecting it onto a line and projecting it onto a W and then projecting it back. This is just a principal component analysis. What this is doing is compute the first principal component of the data. So here, just to see why this is so, right? I have, what is W in this case? What is the dimensionality of W? What's W? So how many is it multiple vectors or a single vector?
Single vector.
This is a single vector, correct? And so here, W is going to be some vector of this kind. And so for any input, X is put through this network, I get some Z, and then this is Z times W, right? Z is going to be a scalar. What does Z times W look like? What will Z times W look like? Z times W is going to be basically different points on this line for different x's, right? So for any x in the input, I am projecting it onto a point on this line. And I'm minimizing the error between the projection and the original point, right? And when I'm training this network, I'm learning the W to minimize this squared projection error. So what is that doing in that case? If I'm just trying to find the direction, where if I expressed everything as just that one direction, what would I be doing? This is the principal component, right? That is classic PCA. You're finding the one principal component that best explains the data. This is what you would be finding. And so if I just had one hidden neuron, I'm going to be performing PCA. And here's the key thing. The W represents one vector. It doesn't matter what the input is. The output is always going to be on that vector because the output is simply Z times W, right? This makes sense to everybody? Okay. Now, if I have, now, it doesn't matter how you compose the network. The output is going to be some Z times W. So regardless of whether the output weights and input weights are the same or not, it's going to learn to perform principal component analysis. Now, if instead of having just one hidden neuron, I had multiple hidden neurons, it's still the same thing. I now have a W matrix. The W matrix can compose a plane. And so when I learn this network, what I'm really learning is the principal subspace, the plane on such that when I project all the data onto this plane, the projection error is minimized. Make sense? And once again, here, so the math will just work out. I just have the math here. X minus W transpose WX squared norm, you minimize it. You're going to find the W, which is basically the principal subspace, right? Represents the basis of the principal subspace. And here's the interesting thing. Once I learn this, because the output is always W transpose X, any vector that I feed in is only going to result in an output that lies on this principal subspace, regardless of what I feed in, right? So here's your next ball. Okay. 15 seconds, guys. Okay. Someone on Zoom, is that first statement true or false? Zoom?
True.
And here, guys, what about the second one? Also true, right? So an autoencoder with linear activations performs principal component analysis of the input. And an autoencoder with linear activations in the hidden layer that has been trained on some data can only output values on this principal subspace. Because regardless of what the value is, the output is simply going to be W transpose X, which only lies on this principal subspace. Right? Everybody's good with that. So again, terminology. The portion of the network that computes this representation in this principal subspace space, that's what we'll call the encoder. It analyzes the input. The portion that can reconstruct the input, basically try to regenerate the data, that's what we call the decoder. So the encoder is going to tell you that on this line, your data point is maybe 3 centimeters from the beginning. But the decoder is actually going to take that value 3 along with this line, create a point in the original space. Right? So now I can introduce a non-linearity. And let's say I begin introducing non-linearities in the decoder. So here, we saw that if the decoder layer has only linear activations, then it can only reconstruct a linear manifold, a linear subspace. But then if you have non-linearities, we saw earlier that non-linearities fold the space, fold the manifold, right? So now the decoder can reconstruct data on curved surfaces. So what the decoder is doing now is to represent the best non-linear manifold to fit the data. And so now what this means is that this decoder can only generate data on this curve. Because that's all. Instead of just doing the line, it's bent the line. Or if instead of having a plane, it's curved the plane. So regardless of, it's found the plane such that when you project the surface, the curved surface, such that when you project all data onto the surface, the projection error is minimized. But then this also has this characteristic that regardless of what I feed in here, the output is only going to be on this surface. So with nonlinearity, this basically ends up being nonlinear principal component analysis, or rather principal manifold analysis. And deeper networks can capture more complicated manifolds. So here are some examples. In this case, we have some data on a spider. And these are two-dimensional data, and then we have this network where it brings the data down to one dimension and then back into two dimensions, the details of the network are on the slide. So now, what is the principal direction of movement for a spiral? It's just movement along the spiral, right? So you would expect that if you learned this right, then out here, what you're going to end up learning is the position along the spiral. And the rest of the network beyond it can only recreate data on the spiral. And so you expect that, and that is indeed what happens, right? You can see that if I feed this data and then train the network, then the recreated data lies only on the helix, only on the spiral. What do you think is happening here? What's going on here? Anybody? What's happening? Anybody? Yeah.
The model messed up and didn't learn the proper features.
So that's not what's happening. It has to do with the training data. There is nothing over here which says that the z values must be continuous, right? So you're expecting that if I have the z value going on, if I have the z going from 0 to infinity, you expect that the output is going to keep going around the spiral. But that doesn't happen. All that happens is that the z is going to make sure that things lie on the spiral in the region where you have training data. If you have a little gap where you don't have training data, then in those z values it can do some funky things. And so here you can see that it goes like so, and then goes this way and then changes direction, right? Furthermore, if the z goes outside the training range, then it goes off and does some strange things as well, right? But within the training space of the training data, it has actually learned the structure of the data. Make sense to everybody? So here's a similar thing with a sinusoid. Same thing. Here, z is the position along the curve, and the decoder can only regenerate data on that curve. Of course, if you go outside the training data space, it goes off linearly. It doesn't continue to create a sinusoid, yeah.
I was gonna like ask, yeah, like how, like the part that it goes off is always linear, or like how is it?
We have no, over here it's not linear, right? It
Yeah,
just did this funky thing, right?
Why did that one like curve off?
Yeah, we have no idea. It's a funky function.
Okay.
So, but anyways, so again, when the hidden representation is a lower dimensionality than the input, we often call this a bottleneck network. It's nonlinear PCA, right? Learns the manifold of the data if it's properly trained. So now this is interesting, this means that if you learn the manifold, that the principal manifold of the data, then the decoder portion of the network can only generate data on this principal manifold. It doesn't matter what you feed it, it's going to generate something on the principal manifold. So for example, if I were to train the network on the digits data, the autoencoder, and then just retain the decoder, then regardless of what I fed it, what came out is going to look something like a digit. Here's an example. This one was an autoencoder where we trained the autoencoder on music from a clarinet. And then we take the decoder and stick some random values here, right? What comes out? I can't hear anything. Wait. You hear some sounds? Let me see. Here's my. Okay, this is on. Aha, the most beautiful portion of the lectures. Okay, let me see this. Paul?
Yeah.
Can I set this up so I can play the audio? It's not playing the sounds out. Got it. So this one has been trained on a clarinet. And then I just take the decoder and give it some random input. I give it a different input. This sounds like a clarinet. Or like a tuba. This one sounds like, here, I've trained this on a clarinet. Let's see what this looks like. Right. So interesting, right? It's sort of learned the manifold on which these data lie. And thereafter, when you just trigger it, it's only able to generate stuff on that manifold, which kind of looks semantically like the data that you trained it with, which is interesting. And so here is a very cute little, first here's a poll. Okay. Can somebody tell me that first statement's true? Can you speak up, say it loud? Second one? And the third? True or false? Somebody on Zoom, is the third statement true or false? Is there anybody on Zoom? I think everybody's missing on Zoom. Okay. Is there anybody on Zoom?
It's true.
Okay, what about the fourth?
It's true.
True. So an autoencoder with nonlinear activation performs nonlinear principal component analysis. It finds the principal manifold, which is the data lie, right? And the decoder can only generate data on this principal manifold regardless of the input. So you can think of it as a dictionary, which composes data like the training data and responds to any input. And so here's a cute little application to close out the lecture, signal separation. I'm given a mixed sound from multiple sources. I want to separate out the sources. So this is a common problem. I give you a recording, music recording. I want to pull out the guitars from the drums, from the vocals. And a common approach is what are called dictionary-based techniques. The basic idea is to learn a dictionary of building blocks for each sound source. So all signals from the source, you model it as being composed from that dictionary. So you'd learn a dictionary, say, for guitars, another dictionary for drums. Then when you got a mixed recording, you'd see how the dictionary entries for the guitar and the drum dictionaries would be combined to compose your mixed signal. And then, the separated contributions of each of the dictionaries is going to give you the separated sources. Now, in our example, so you can recompose these separated sources. So in our example, how does that work? If I wanted to separate guitars from drums, I could learn an autoencoder for guitars. I could learn an autoencoder separately for the drums. And now, the decoder for the guitar can only produce guitar-like sounds. The decoder for the drums can only produce drum-like sounds. If I have a mixed signal, the mixed signal has both drums and guitars. So it means that this mixed signal has been produced by adding up something that has been produced by my guitar decoder and something that has been produced by my drum decoder. So if these two decoders have been separately trained already from guitar and drum data respectively, then when I'm given a mixed signal, I can use backpropagation to find out what inputs must go into these two decoders such that their outputs sum up to the mixed signal that I have. And then subsequently, so that's what I do. I'd have the mixed signal. I use backpropagation to find out what these inputs must be such that the output of this decoder and this decoder, when summed up, give you the mixed signal. And then the output of this decoder alone is going to be just the guitar. The output of this decoder alone is just going to be the drum, because they can only compose the drum and the guitar respectively. So let's see how this works, right? Here's an example. Again, this is a very trivial thing that we're doing. These were 5-layer networks, 600 units wide on the decoder side, the dictionaries. Here's a mixed recording. There's a wind instrument and a string instrument. For here's the original premix. And here is the other one. And this is as you can see, does a pretty good job, right? Again, giving us the idea that confirming our hypothesis that if you train these networks properly, then what the networks also do is to learn the manifold that the data lie on principally. And when we perform classification, it's performing linear classification on this manifold. When you're performing reconstruction, it's reconstructing data on this manifold. That's what we're doing for the autoencoder. And this is what we're going to use in subsequent lectures for generative models. So the story for the day, classification networks learn to predict a posteriori probabilities for classes. The network until the final layer is a feature extractor that converts the input data to be more or less linearly separable. And the final layer is a classifier or predictor that operates on the linearly separable data. The networks can also be viewed as performing nonlinear principal component analysis. So you can in fact use these to reconstruct data in the form of autoencoders, which can be used to compose constructive dictionaries for the data, which can be used to model data distributions. We'll follow up on this in the next class. Thank you.